Figure 6 shows a sketch of the curve C with parametric equations x equals 2 tan t plus 1, y equals 2 sec squared t plus 3. Note here that t is defined between negative pi by 4 and pi by 3, giving us distinct endpoints, and that's going to be important later in the question. In part A, using parametric differentiation, show that an equation for L is y is negative a half x plus 17 over 2. So we're going to need to do some calculus. We need dx dt. Tan differentiates to sec squared, so that one's going to be 2 sec squared t. And it might be worth noting, although we should know this, that that's 2 over cos squared t. Then dy dt is a bit more complex. So when we have sec squared t, remember what that means is sec t squared. So differentiating, we're going to get 2 sec t to the power 1, but chain rule means we need to multiply by the differential of the inside. Differentiating sec gives us sec t tan t. So this ends up being 4 sec squared t tan t. Now let's think about what sec and tan are. So that is going to be 4 over cos squared t, and tan is sine t over cos t. So that is 4 sine t over cos cubed t. Now we want dy dx, which is dy dt divided by dx dt. So it's going to be 4 sine t over cos cubed t divided by 2 over cos squared t. So that's 4 sine t over cos cubed t multiplied by cos squared t over 2. Simplifying that gives us 2 tan t. Cos squared will cancel with some of those. 2 will cancel with that, like so. And so dy dx, given that t is equal to pi by 4, is going to be 2, tan of pi by 4 being 1. And that means the gradient of the normal is going to be negative 1/2. Now we could do with the coordinates of p here, and p is when t is pi by 4. So that's going to be 2 plus 1, so the x-coordinate there is going to be 3. Now sec squared t we know is, so that's 2 over cos squared t plus 3. So if t is pi by 4, we have cos of pi by 4 is 1 over root 2. If we square that, that's a half. So 2 divided by a half is 4, add 3 gives us 7. Now the way I like to work these out usually is using y minus y1 is mx minus x1. And so the y coordinate there was 7. That's negative a half. X take away 3. So y take away 7 is negative a half x plus 3 on 2. And so we have y is negative a half x plus 3 on 2 plus 14 on 2, which is the 7 moved over. And that is negative a half x plus 17 on 2 as required. So moving to part B, we want to show all points on C satisfy this equation here. Now note that's a Cartesian equation, so it's a case of eliminating the parameter of t. So let's start with y. Y is 2 sec squared t plus 3. Now we know that tan squared plus 1 is equal to sec squared. So y is going to be 2 tan squared t plus 1 plus 3. So that's going to be 2 tan squared t plus 5. Now, tan t is going to be x take away 1 on 2. So y is going to be twice x take away 1 on 2 squared plus 5. We can write that as 2x minus 1 squared on 4 plus 5, giving us a half x minus 1 squared plus 5 as required. We're now told the straight line with the equation y equals negative half x plus k, where k is a constant, intersects C at 2 distinct points. Find the range of possible values of k. There's 2 things here. First of all, we've got this end point. I did say that these would be important. It can only intersect at 2 places if it's lower than that point. And then there's going to come a point where it goes through the turning point, and then we get no more solutions. So, what we are going to do, first of all, is consider the end point here. So, that's going to be when t is negative pi by 4. So, the x value is going to be 2 tan negative pi by 4 plus 1. So, that's going to be negative 2 add 1. So, it's negative 1. At pi by 4, we're going to get 2 over cos negative pi by 4 squared plus 3. So cosine of negative pi by 4 is 1 over root 2. Square that, so it's 2 over a half plus 3. So 4 plus 3 is 7. So that's the end point just there. So the line that we have is y is negative a half x plus k. So put that in. 7 is equal to negative a half times negative 1 is positive a half plus k. That gives me k is 13 over 2. Now, as the line moves down from there, k will reduce. So we know that k needs to be less than or equal to 13 over 2. That's part of the answer. The other part of the answer comes from looking at a half x minus 1 squared plus 5 is negative a half x plus k. So that is going to give me x minus 1 squared plus 10, I'm just multiplying through by 2, is negative x plus 2k. Expanding out, x squared minus 2x plus 1 plus that 10 is 11 is negative x plus 2k. So x squared minus x plus 11 minus 2k is equal to 0. And we want that quadratic equation to have 2 solutions. So we're going to use the discriminant. B squared minus 4ac is going to be 1 take away 4 times 1 times 11 minus 2k is greater than 0. So that's 1 take away 44 plus 8k is greater than 0. That gives me 8k is greater than 43, and so k is going to be more than 43 on 8. So putting those together, k is going to be more than 43 on 8 and less than or equal to 13 on 2.